Welcome to the Copper Spice YouTube channel, and thanks for joining us. We're doing a two-part video series on Unicode and our Unicode-aware string library. CsString library, part 1.
Before we talk about our Unicode-aware string library, we need to talk about some string terminology. We'll also discuss Unicode itself and how some other libraries handle strings.
The first term we need to define is a character set. A character set is nothing more than a collection of symbols. It does not associate any values, and it's completely unordered. A character encoding is what associates the symbols in a character set with specific values. This term is a bit confusing because there actually isn't an encoding. It is just an association. A better term is a character map.
A coded character set is a defined standard that includes both a character set and a character map. So it consists of a well-defined set of symbols and the values that they map to. Notable examples of this that many programmers will have used include ASCII and ISO 8859-1. These are both coded character sets, which contain a fixed set of symbols and their associated values.
The fundamental term we need to define in order to understand strings are code points. They're sometimes also referred to as a code position. Code points are not the same as a character. A code point is the atomic unit of text, and it is a 32-bit integer.
The term code unit refers to the way in which code points are stored when they are represented in memory. There are many different encodings that have different sized code units. So for example, in UTF-8, the code unit is an 8-bit integer. And in UTF-16, the code unit is 16 bits. Another term that we need to define is the basic multilingual plane. These are the first 64K code points in Unicode. These cover the vast majority of all modern human languages in use today. And these are exactly the set of characters which fit into 2 bytes in the UTF-16 encoding. I mentioned ASCII briefly earlier. ASCII is a 7-bit coded character set, which has been around for a long time. It's important to understand that ASCII consists of only 128 characters because it's a 7-bit character set. These first 128 characters exactly match the first 128 code points in Unicode. There is a lot of confusion surrounding the use of the term ASCII. Strictly speaking, ASCII refers to the first 128 code points, and there are many other coded character sets which contain ASCII as a subset. It's important to distinguish those from ASCII itself.
Latin 1 is an 8-bit coded character set. The first 128 code points in Latin 1 are the same 128 characters that you would find in the ASCII coded character set. You will find other Latin character sets which support languages spoken in Central Europe. So let's take a look at some examples of how characters are actually encoded. The Latin capital letter A has a value in Unicode of U plus 0041. If you were encoding this in UTF-8, it would be represented by exactly 1 byte. In UTF-16, it would take 2 bytes. This is still 1 code point and 1 storage unit, regardless of if you are using UTF-8 or UTF-16. Another symbol is the rightwards arrow with corner downwards. It is also 1 code point, and it has a Unicode value of U plus 21B4. In UTF-8, this takes 3 bytes and 3 storage units. If you were encoding it in UTF-16, it is represented by 2 bytes and 1 storage unit. The important takeaway is that each of these symbols is a single code point, no matter which encoding is being used.
Another example is the musical symbol 8th note. It has a code point value of U plus 1D160. And since this code point value requires 5 hex digits to represent, we know it's outside the basic multilingual plane. In UTF-8, this symbol is represented by 4 bytes, which is 4 storage units. In UTF-16, it is represented by 4 bytes in 2 storage units. It is always one code point and a variable number of storage units depending upon the encoding.
Unicode code points are always 32 bits. In each of the 3 examples we just showed, each one has a 32-bit value, but not all the bits are used. This explains why using a 32-bit encoding would be quite wasteful.
One of the common variable length encodings in use for Unicode is UTF-8. It is a very efficient encoding, since there are a good number of code points which only require 1 byte to represent, as opposed to UTF-16, which has a minimum of 2 bytes for any code point. Since the storage units used in UTF-8 are individual bytes, there is no need to be concerned about the endianness of your architecture and the way that integers are represented. When encoding a string in UTF-8, you will need to calculate how many bytes are required to store an individual code point. And this process is more straightforward than in UTF-16.
UTF-16 is also a variable length encoding. Many people tend to think that UTF-16 is exactly one storage unit. It is not. There are times when a code point will require 2 storage units in UTF-16. UTF-16 is actually the worst choice for encoding, since many code points require multiple storage units, and it is wasteful and too wide for the majority of Latin characters, since a single storage unit is 2 bytes. Companies like Microsoft adopted UTF-16 back in the early days of Unicode. It seemed like a very attractive option since most code points do require a single storage unit in UTF-16.
Operating systems like Linux, which adopted Unicode much later, saw the struggles that Windows developers went through in working with UTF-16 and realized that UTF-8 was a better option.
Joel on Software is a blog that's been around for quite a while. This is a direct quote taken from 2003. His point is that if you have a string and you don't know the encoding, you don't know what that string says.
For a historical perspective, we'd like to note that the first version of Unicode used an encoding called UCS2. It was a 16-bit storage format, 2 bytes per code point, and fixed width, because at that time, Unicode had not yet grown to a 32-bit code point. In 1993, they realized that 16 bits was not sufficient for the number of code points that would be required. So they expanded Unicode to 32-bit code points and developed the UCS4 encoding. When Java adopted Unicode in 1995, it used UCS2 as its string representation. It wasn't until 1996 that variable width encodings were standardized in Unicode, and UTF-8 and UTF-16 became part of the standard. In 2005, 12 years after Unicode made the transition to a 32-bit code point, Java version 5 added support for UTF-16.
Many languages that say they support UTF-16 actually support UCS2. It is important to know the character encoding supported by the language and libraries you are using and how they deal with code points, especially those code points that are outside the basic multilingual plane.
So let's ask what support is provided for Unicode in the C++ standard library. And the answer is none. Neither stdstring nor stdwstring provide any mechanisms for specifying encoding. They do not deal with variable length encodings in any way, and they provide no support for the developer to implement either UTF-8 or UTF-16. Most languages and libraries do not support UTF-8, and those that support UTF-16 often have issues with variable length encoding. For example, in C#, If you declare an input field widget, you can specify how many characters you want the user to be able to type in the input field. However, rather than being in units of characters, it's actually in units of storage units, which means if you specify a limit of 10 characters, and the user types 9 characters, and then 1 character which requires 2 storage units to represent, the first half of the code point will be inserted, an error will be thrown, and in trying to report the error and print the malformed UTF-16 string, the .NET runtime will crash. This is an example of how important it is to have native support for UTF-16 variable length encoding in your language and library. So here's a problem we ran into in the development of DoxyPress. The original code that was implemented for text processing used a very old Qt string class. These classes used 8-bit storage and had no facility for storing the encoding. They were roughly equivalent to std string in their functionality, with the added complexity that they were implicitly convertible to a character pointer. We refactored this legacy code that was using CsString and QGstring to use the QString class from CopperSpice, which is a UTF-16 string class.
Here's an example of what happened as we started to use QString. We have a variable called text, and it's going to be passed to a method and then passed again to another method so it can be printed out on the screen. Since this text might not be in English, we decided to test it in both German and Russian. This code needs to work regardless of the language that the text is in. We didn't notice any problems when the text was in English. But as we started to test for German and Russian, things did not turn out so well. The German text you see on the screen isn't actually correct, but it's vaguely readable. The Russian one is completely gibberish. The carriage returns you see in the Russian actually appeared on the screen. We did not add them for the benefit of this slide. So the question is, what went wrong?
And the answer is, when you do not know what encoding a string is in, you cannot safely work with it. When we call M1 here, we are passing the data as a const character star. Data refers to a string which is encoded in UTF-8, but there is no way that M1 can know what encoding the string is in. When M1 calls M2, a new QString is constructed for the call. The QString constructor assumes that the input is Latin 1. At this point, all of the text outside of the basic ASCII 128 character set is completely mangled. This underscores how important it is to have a string library that implements Unicode fully and properly, and to use it consistently throughout your entire program.
In our next video, we're going to talk about the internals of CsString and how we've integrated this library with CopperSpice and how you can use the CsString library in any C++ application.
For more information about CopperSpice and the CsString library, please visit our website at www.copperspice.com.
Thanks for watching our video. We hope you found the content of value. If you have any questions, feel free to email us or leave a message on our CopperSpice form. We'd love to hear from you.
Please make sure you subscribe to our YouTube channel and come back in 2 weeks for our next video.